We've built the whole toolbox: limits, L'Hopital, continuity, derivatives, Taylor series, and finding the biggest and smallest. Today, we don't learn a new tool. We learn to reach for the right one. Because the hard problems rarely need heavy machinery. Almost everyone turns on a single insight. The one thing you notice that makes it fall apart in your hands. 5 problems. 5 clean insights. Watch how each one cracks. Then, at the end, we'll collect the moves. The small handful of habits that quietly solve almost everything. Problem 1. The limit, as x goes to 0, of tan x minus x all over x cubed. Substitute 0, and you get nothing but 0 over 0. The classic dead end. You could reach for L'Hopital, but you'd have to differentiate 3 times, and it gets ugly fast. Here's the insight. Near 0, tan x isn't mysterious. It has a series. And a series turns this into simple cancellation. The series for tan x begins x plus x cubed over 3 plus a tiny x to the 5th term and on. Subtract the x, and the leading x vanishes. The smallest survivor is x cubed over 3. Now the numerator and the denominator both start at x cubed. Divide every term by x cubed, and the leading piece becomes 1/3, while everything else still carries a factor of x squared. Let x go to 0. Every leftover term dies, and the answer is simply 1/3. No triple differentiation. The series did all the work. And here's the picture that makes it obvious. Plot the real numerator, tan x minus x, in white. Now, overlay x cubed over 3 in gold. Watch. Near 0, the two curves are practically the same line. That is why, deep in the limit, the numerator behaves exactly like x cubed over 3, and the ratio settles on 1/3. Problem 2. A conceptual trap. Is the function f of x equals x times the absolute value of x differentiable at 0? The absolute value has that famous sharp corner, so instinct screams no. But instinct is wrong here, and the insight is a rule we can never skip. At a suspicious point, check both one-sided slopes. If they agree, it's smooth. If they clash, there's a corner. Let's actually look. First, rewrite it without the bars. When x is positive, x times x is just x squared. When x is negative, it becomes minus x squared. So the graph is a parabola on the right, flipped through the origin on the left. Now the slopes. On the right, the derivative is 2x, which slides to 0 as x approaches the origin. On the left, it's minus 2x, which also slides to 0. Both sides arrive at the same slope, 0. They agree. So despite the absolute value, the curve slips through the origin perfectly flat, with no corner at all. F is differentiable, and f prime of 0 is 0. The plain absolute value would have failed. Its slopes are -1 and +1. Multiplying by x smooth the kink away. Problem 3. An optimization with a picture. Under the downward parabola y equals 12 minus x squared, we inscribe a rectangle sitting on the x-axis. Which one has the greatest area? Let the corners on the right sit at x equals a. So the two top corners write the parabola at height 12 minus a squared. The width is 2a, the height is that. Watch the area as it grows. Too thin, and there's no width. Too wide, and the height collapses toward the ground. The best rectangle is somewhere in between. Let's pin it exactly. The area is width times height, 2a times 12 minus a squared, which is 24, a minus 2a cubed. One variable, so just differentiate. A prime is 24 minus 6a squared. Set it to 0, and a squared is 4. So equals 2. Confirm it's really a maximum. A double prime is minus 12a, which at a equals 2 is minus 24, comfortably negative. A dome. So yes, a genuine maximum. So the winning rectangle has a equals to width 4, height 8, and a maximum area of 32 square units. There it sits, snug under the parabola, the biggest box the curve will allow. Problem 4. Estimate the cube root of 8.1. By hand, no calculator. It looks awkward because 8.1 isn't a perfect cube, but 8 is a perfect cube. Its cube root is exactly 2, and 8.1 is just a whisker away. The insight: near a point we know, a smooth curve looks like its tangent line. Write that tangent, the last tiny step. Set f of x equal to the cube root of x, centered at a equals 8. We know f of 8 is 2. The derivative is 1/3 x to the minus 2/3, which is 1 over 3 times the cube root of x squared. At 8, the cube root of 8 squared is the cube root of 64, which is 4. So f prime of 8 is 1 over 3 times 4, 1 over 12. That's the slope of our tangent. The linear approximation says f near a is f of a plus the slope times the small step. Our step is not 0.1. So the cube root of 8.1 is about 2 plus 1/12 of a tenth. 1/12 of a tenth is about 0.0083. Add it to 2 and we get 2.0083. The true value is 2.00830. We nailed 4 decimal places by hand. And here's why it works so well. The cube root curve in white and its tangent at the point 82 in gold. Right around 8. The two are almost indistinguishable. So walking along the straight tangent for that last little step lands you essentially on the true curve. That is the whole idea of a linear approximation. Problem 5 is my favorite. It looks impossible. We're told nothing about f except one inequality. The gap between any two outputs is at most 4 times the gap in inputs squared. No formula. And yet, find f of 5 minus f of minus 2. With no formula, where do you even start? Here's the insight, and it's a beauty. That little square on the right is unbelievably strong. It forces the function to be completely flat, a constant. Watch how one division proves it. Start from the inequality. For any two different points, divide both sides by the size of x minus y. On the left, that ratio is exactly the difference quotient, the average slope between the 2 points. On the right, 1 power of x minus y survives, so we're left with 4 times its size. Now let y slide toward x. The right-hand side, 4 times the shrinking gap, is squeezed straight to 0. But the left-hand side is heading for the very definition of the derivative. So the absolute value of f prime is trapped at 0. And a function whose derivative is 0 at every single point cannot go anywhere. It must be a flat constant. Call it k. That's the whole game. So f of 5 and f of minus 2 are both just k. Their difference is k minus k0. From a single inequality with no formula anywhere in sight, a clean, exact answer, 0. Picture it. The squared bound pins the slope to 0 everywhere. So the only graph allowed is a perfectly level line. Whatever height it sits at, f of 5 and f of minus 2 are the same value, and their difference is nothing at all. Your turn, and it's a cousin of the last one. A function on the interval 0 to 3 has a slope never bigger than 2 in size. How far apart can f of 3 and f of 0 possibly be? Pause the video, think about what a bounded slope allows, and find the largest gap. I'll wait. Here's the walkthrough. The insight is the mean value theorem. Somewhere in the interval, f of 3 minus f of 0 equals the slope at some point c times the width 3. So the gap is 3 times that slope. Take absolute values. Since every slope is at most 2, the gap is at most 3 times 2, 6. And it's genuinely reachable. The straight line f of x equals to x has slope exactly 2 and gives f of 3 minus f of 0 equal to 6 on the nose. So the largest possible gap is 6. Notice the contrast with problem 5. There, a squared bound crushed the difference to 0. Here, a plain slope bound leaves real room, up to 6. If you saw that, you're thinking like a problem solver. Step back, and every problem today used one of a small handful of moves. These are the reflexes. The whole calculus toolbox was really teaching. Keep them close. For any limit, always substitute first. If it's a clean number, you're done. Only when you hit 0 over 0 do you choose a weapon, factoring, L'Hopital, or a Taylor series. For continuity or smoothness at a suspicious point, check both sides. If the one-sided values or slopes disagree, there's a break or a corner. Exactly the x times absolute x trap. For a maximum or minimum, set the derivative to 0 for the candidates. Then never forget to test the endpoints and the second derivative before you commit. For a hard limit or a by-hand estimate, reach for a Taylor series. It turned a triple L'Hopital limit into a one-liner and a cube root into mental arithmetic. And for shape or a strange inequality, let the derivative speak. A squared bound forced a constant. The second derivative decides every dome and bowl. Master these 5 reflexes, and calculus stops being a pile of rules. It becomes a way of seeing,